Okay, today we're going to talk about equations with constant coefficients. And what we're really going to be doing is, if we've got constant coefficients, then how do we handle the roots with multiplicity? Okay, so let's start off with reminding you of a few things. Remember that if you take the first derivative of y and it's equal to 0, then that means our equation y must have been a constant, right? It's a constant function if, when you take the first derivative, you end up getting 0. If you take the second derivative of y and that's what gives you 0 instead, right? Then that means that your equation y must have been a linear. So c1 plus c2 x to the power of 1, right? It must have been well, I'll say if your equation was a linear equation, taking the second derivative is what will bring you to 0. The third derivative on y, if that's equal to 0, then your y must have been a quadratic, right? You could have a constant plus c2 times x plus c3 times x squared. It was a quadratic. And taking the third derivative of a quadratic will give you 0. All right, so remember those. And then from section 2, we learned that if we have this polynomial operator, d minus 1 on y, if that's equal to 0, do you remember our auxiliary equation was r minus 1, so we had a root of 1, and that meant that our equation was y equals some constant times e to the x. Look back on section 2 if that does not sound familiar. And then we also learned, so that was a real root, right? We also learned that if your roots were complex, right? So you had a quadratic that, an irreducible quadratic, which meant that you had, if you've got a plus and minus bi, if those guys were roots, then our general equation was y equals c1 e to the ax cosine of bx plus c2 e to the ax times sine of bx. Right? So that's what we've learned so far, was when they were real, when they were complex roots, how to handle them, what were the general solutions. Now, what are we going to do when there's multiplicity on those roots? So now let's look at what happens. What I mean by multiplicity is, what if it's not d minus 1 on y? What if it's d minus 1 quantity squared on y? How do you handle ones like that? How do you handle it if there is multiplicity on the root? So let's start with our theorem. So given a real polynomial p, then it's 3 parts. First of all, if r is a real root, so like from 5-2, right? That was a real root. If it's a real root, but now what if it has multiplicity on it, right? So a real root of multiplicity k. Multiplicity k of p. Then for all j, where j goes from 0 to k minus 1. K is the multiplicity, you'll go to 1 less, right? Then y is going to equal x to the j times e to the rx. This is a real solution to the differential equation p of d operating on y is equal to 0. All right, so here, that's how we handle real roots with multiplicity, right? So here's a quickie example. What if 7 is a root of multiplicity 4? Right, if 7 is a root of multiplicity 4. I mean, just as a side note, that means that we would have started with a d minus 7 and then to the 4th power, operating on y will equal 0, right? That's what that means. Your root would have been 7, but the 4 means you've got a multiplicity of 4 on there. All right, so that means your r is 7, but then with a multiplicity of 4. So the solutions, so what this part 1 of this theorem tells us is that the solutions for this r value are, you would have x. You're going to start with j and include all of the j's until you reach 1 less than the multiplicity. So we'll have x to the 0, e to the 7x. Another solution, x to the 1, e to the 7x. X squared, e to the 7x. And x cubed, e to the 7x. I'm stopping at x cubed because that's 1 less than my multiplicity of 4. All right? That's what that theorem says. Well, part 1 of that theorem, right? Part 2 of the theorem talks about how to handle it when your roots are complex and there's multiplicity. So if a plus bi, where b is not 0, is a complex root of multiplicity k of p, then we also know a minus bi is also a complex root of multiplicity k of p. All right. And for all j, where j is going to go from 0 until 1 less than the multiplicity, k minus 1, then y equals x to the j, e to the ax cosine of bx, and y equals x to the j, e to the ax sine of bx, are both real solutions to the differential equation p, the polynomial operator on y, is equal to 0. All right, so I'll give you a quick little example of that one. So example on part 2 is that, if 3 plus or minus 4i are roots of multiplicity 3. Right. Then the solutions would be what? Well, for 3 plus or minus 4i, over this line, that's saying that your a is 3 and your b is 4, right? And now we've got a multiplicity of 3, so we're going to add in these x powers on x, multiplying times them. So that means our solutions will be, you would have x to the 0, e to the 3x cosine of 4x. You would have x to the 0, e to the 3x sine of 4x. Yeah. You would have x to the power of 1, e to the 3x cosine of 4x, x to the power of 1, e to the 3x sine of 4x. And you would also got multiplicities of 3, so you're going to go from 0, you're going to use 0, 1, and 2 as the exponents on x. X squared, e to the 3x cosine of 4x. And and x squared e to the 3x times sine of 4x. Those will be the roots or the solutions, right, to if we had 3 plus or minus 4i as roots with a multiplicity of 3. All right, and then part 3 of this theorem states that all solutions of either type are linearly independent. And so that means what we're going to do is we're going to write our solutions as a linear combination of all of these individual solutions. And linear combination means we're going to have constants times each of them. All right, so let's do some examples. Let's directions. Solve the following differential equations. We're finding the general homogeneous solution. So the general homogeneous solution would be taking a linear combination of each of these guys, adding them together. You know, multiplying their constant times each of them and adding them together is what our general homogeneous solution will be. All right, so example 1, let's solve d minus 1 to the power of 5 on y is equal to 0. Well, this means that for my auxiliary equation would be r minus 1 to the power of 5. So your root is 1, but with a multiplicity of 5. Yeah, so your solutions, this is from the part 1 guy, right? Your solutions will be x to the 0, e to the 1x, x to the power of 1, e to the 1x, x squared, e to the 1x, x cubed, e to the 1x, x to the 4th, e to the 1x. I'm stopping because 4 is 1 less than that multiplicity of 5, right? And so your general homogeneous solution will be y equals, and you'll just do a linear combination of these guys. X to the 0 is just 1, so I'm not going to write a 1. And also on all of these e to the 1x, I'm not going to include the 1 anymore. It's just a C1. The constants I'm going to use, by the way, are C1, C2, C3. So I'm just going to use C's with little subscripts for each of them. So this is C1, e to the x, plus C2x, e to the x, plus C3x squared, e to the x, plus C4x cubed, e to the x, plus C5x to the 4th, e to the x. That is our general homogeneous solution to that differential equation. All right, let's do another example. How about d squared plus 1 all to the 3rd power operating on y is equal to 0. All right, so what would our auxiliary equation be? It would be r squared plus 1 cubed. That's what we want to solve for, right? So r squared plus 1 would give me that r is equal to plus or minus I, but we have a multiplicity of 3 coming from here. That's where the multiplicity is given you. And I solved r squared plus 1 equals 0. Subtract the 1, take the square root, you got plus or minus I. So for plus or minus I, that means your a is 0, your b is 1, and then of course from here, your k is 3, because that's the multiplicity. And so your solutions would be what? Well, they would be x to the 0, e to the 0x cosine of 1x, and x to the 0, e to the 0x sine of 1x. Yeah. And then x to the 1, we got multiplicity of 3, so I need to go x to the 0, x to the 1, and x squared. x1, e to the 0x cosine of 1x, and x to the power of 1, e to the 0x sine of 1x, and x squared, e to the 0x cosine of 1x, and x squared e to the 0x sine of 1x. Yeah. And so your general homogeneous is going to be a linear combination of all 6 of these guys. So your general homogeneous solution would be y equals C1, x to the 0 is 1, e to the 0 is 1, so it's just C1 times cosine of x plus C2 times this guy, which turns out to just be sine of x, plus C3, x times cosine of x, plus C4, x times sine of x, plus, and I'm going to run out of room. I'll come down here. C5, x squared cosine of x plus C6, x squared sine of x. All right. General homogeneous solution, linear combination of all of those guys. All right, let's do another example. How about d plus 4 to the third times d plus 1 squared operating on y will give you 0. All right, so our auxiliary equation would be an r plus 4 cubed times an r plus 1 squared is equal to 0. This guy would give me a root of -4, but with a multiplicity of 3. This guy would give me a root of -1 with a multiplicity of 2. So both of these roots are real. Yeah, nice. They just have multiplicities on them. No big deal. So your solutions will be what? Well, this first guy will give you x to the 0 e to the -4x, and then x to the power of 1 e to the -4x. It was a multiplicity of 3, so you got to go to x squared e to the -4x. The solutions on this guy would be an x to the 0 e to the -1x, and x to the power of 1 e to the -x. Stopping because you got a multiplicity of 2, you'll go one less. And so that general homogeneous solution is the linear combination of all of these guys. So y equals C1 e to the -4x plus C2 x times e to the -4x plus C3 x squared e to the -4x. That's from the first factor. And then we'll include these guys. So plus C4 e to the -x plus C5 x times e to the -x. There you go. All right, let's do another example. How many do I have here? Dang. All right. Got some more for you. Okay, example 4 is, what if I don't give it to you with these like polynomial operators? What if I say to you, oh, solve y triple prime, right? The third derivative on y plus 2 times the second derivative of y plus the first derivative on y plus 2 times the actual y value itself is equal to 0. Solve this differential equation. Okay, so when they give it to you like this, I'm going to change it to a polynomial operator. Remember that the third derivative on y is d cubed. This would be 2 times d squared plus 1 times d. That's technically to the power of 1. And then plus 2 operating on y. Yeah. All right, so now I want to factor these guys. So I see 4 terms. I'm going to factor by grouping, which means I would, out of these first 2, I've got a d squared in common, which would leave me with a d plus 2. And to factor by grouping, oh look, I got a d plus 2 there. So if you factor out a 1, we'd have a d plus 2. And your parentheses match, so that's one of your factors. And the other one is d squared plus 1. Coming from, when you factored out the d plus 2, you'd have a d squared. Factoring out the d plus 2 here would leave you with a plus 1. So that's where the other factor's coming from. All right, I got it factored. That means my auxiliary equation is an r plus 2 times r squared plus 1 equals 0. So this first one will give you an r equals -2, and this guy will give you an r equals plus or minus I. And both of these guys only have a multiplicity of 1. The multiplicities come from the exponents on the factors, right? So I know you see an r squared here, but that's not a multiplicity. It would have a multiplicity if it had an exponent on the factor on the outside of the parentheses. The r squared on the inside, with that being a plus sign, gives me the complex roots there. Okay, so that guy's real, yeah? So that means that its solution for this guy is just e to the -2x. Yeah. This guy, complex, your a would be 0, b is 1, and so you'd have an e to the 0x cosine of 1x and an e to the 0x sine of 1x for those 2 roots. And your general homogeneous solution is y equals the linear combination of all 3 of these guys. So we've got c1 e to the -2x plus c2 e to the 0 is just 1, so I don't need to write that. And then plus c3 sine of x. Good? Now, obviously, you could have, like, had you written this, factored it the other way, right? You may have come up with these guys first. So this, where the C1, C2s, and C3s are don't matter, right? It could have been C1 cosine of x plus C2 sine of x plus C3 e to the -2x. Obviously, it doesn't matter. So, yeah, you just want a linear combination of the 3. Okay, let's do another example. All right, example 5. How about d squared minus 2d plus 5 quantity squared operating on y equals 0? All right, so your auxiliary equation would just be r squared minus 2r plus 5 squared equals 0. That means you're going to have a multiplicity of 2 here. You got to factor this guy. 2 numbers that multiply to 5 and add a -2. Not going to happen. But you can use quadratic formula. That'll work every time. The -2 on here is easy to complete the square, so that's how I'll do it. R squared minus 2r, leave a little space, subtracting the 5 over. Taking -2, cutting it in half would give me -1. Squaring that will give me a +1. So as long as I add it to both sides, that works. This is an r minus 1 quantity squared is equal to -4. Which means when you take the square root of both sides, you'll have a plus or minus. Square root of -4 is 2i, and then adding the 1 over, you'll have 1 plus or minus 2i are your roots, yeah, where your a is 1 and b is 2, but from here, we've got a multiplicity of 2. So your k is 2. All right, so that means your solutions are, they're both roots are complex, right? And a multiplicity of 2. So they'll be an x to the 0, e to the 1x cosine of 2x, and x to the 0, e to the 1x sine of 2x, x to the power of 1, e to the 1x cosine of 2x, and x to the power of 1, e to the 1x sine of 2x. Stopping there, multiplicity of 2, so you'll include x to the 0 and x to the 1. And our general homogeneous solution will be the linear combination of all 4 of these guys now. So the general homogeneous solution is y equals c1 e to the x cosine of 2x plus c2 e to the x sine of 2x plus c3 x e to the x cosine of 2x plus c4 x e to the x sine of 2x. Looks good to me. All right. Let's do another example. Because I'm just full of examples today, apparently. All right. How about if I ask you to solve the differential equation, the 4th derivative on y plus 8 times the third derivative, just kidding, that's 3, plus 20 times the 2nd derivative of y is equal to 0. All right, so I'm going to rewrite it as a polynomial operator. This would be d to the 4th plus 8d cubed plus 20d squared operating on y is equal to 0. Your auxiliary equation would be r to the 4th plus 8r cubed plus 20r squared equals 0. And we want to solve for r. So I notice there's an r squared in common to all 3 terms. I'll factor that out. Now, all right, that means that r squared is equal to 0. 20, multiplying to 20 and adding to 8, not going to happen. All right, it's okay. All right, so I set each factor equal to 0. So r squared equaling 0 means that r equals 0, but with a multiplicity of 2. So that's a real solution, right? But it has a multiplicity, so your 2 solutions will be x to the 0, e to the 0x, and x to the power of 1, e to the 0x. This guy, you're not going to find 2 numbers that multiply to 20 and add to 8. 8's an even number, though, so I can complete the square easily. Subtract that 20 over to the right-hand side of the equation. 8 cut in half is 4. 4 squared is 16. So that's an r plus 4 quantity squared is equal to negative 4, which will give you r plus 4 is equal to plus or minus 2i, and r would be negative 4 plus or minus 2i, which means that your a is negative 4, your b was 2, and this factor didn't have a multiplicity on it. There was no exponent on the outside of those parentheses, so it's just multiplicity of 1. So that means that our solutions will be just e to the negative 4x cosine of 2x and e to the negative 4x sine of 2x. Those will be your 2 solutions. So I've got 1, 2, 3, 4 solutions. Your general homogeneous will be combining all 4 of these solutions together in a linear combination, so that your general homogeneous would be y equals c1 x to the 0 times e to the 0. That's just 1. So it's just c1 times 1 technically. All right, that's just 1. So c1 times 1 plus C2 times x, and then e to the 0, that's just x. Okay, nice. And then plus C3 e to the negative 4x cosine of 2x plus C4 e to the negative 4x cosine, not cosine this time, it's sine. Got this? Sine 2x. There's your general homogeneous solution to that differential equation. Okay. Are you ready right now to find out why last year's multivariable students or linear algebra differential equation students called me the annihilator? This is why. You're going to find out what the annihilator means. Definition. A polynomial operator UD is called an annihilator. Annihilator of the function y equals f of x if and only if when that polynomial operator is operated on y, it annihilates it. It brings it to 0. So last year when I was teaching them, I was like, annihilator. Like, ooh, that's a good nickname. Like, maybe I should change my nickname to the annihilator. Annihilating, they're like, yeah, because you annihilate our grades. I'm like, not really. But anyway, there you go. That's why my little plaque that they gave me calls me the annihilator, because I had joked about how I wanted my nickname to be the annihilator. Okay. So yeah, all the annihilator, it's what brings that function down to 0. What polynomial operator will annihilate the function and bring it to 0. All right, so for example, we'll do some quick examples of if y equals e to the 2x, what's the polynomial operator that would bring that to 0? And so here's what I noticed. I noticed that if you take the first derivative on e to the 2x, remember it's e to the 2x, but then chain rule would say times 2. So it's 2 times e to the 2x, which you could do a linear combination of these guys, and it'll bring you to 0. You see that? That means that if I were to take y, the first derivative on y, 2e to the 2x, and subtract from it 2 times this guy, that will give me 0. Yeah? And so the annihilator of this function is t minus 2. Yeah. All right, another quick example. What if your function is x squared? Yeah. So this one, because your derivatives on e just keep looping, right? We had to do it this way. This one on x squared, if you keep on taking derivatives, it will bring you to 0. And so that's what I'll do on this one. I know the first derivative would be 2x. I know the second derivative would just be 2. And then the third derivative would be 0, right? So then that means that the annihilator of x squared is d3, because it's the third derivative that will bring x squared down to 0. Make sense? The annihilator. Doesn't it just sound like the coolest nickname ever? I think so. All right, but I'm a math nerd, so whatever. All right, show that the polynomial operator d squared plus 4d plus 5 annihilates. Right? Yep. The function y equals 4e to the negative 2x times sine of x. All right, so if this guy annihilates it, then that means that when I take the second derivative of y, add it to 4 times the first derivative, and add it to 5 times the function, you'll end up getting 0. So what do I need? I already have y. I need the first derivative, and I need the second derivative of this function. All right, so let's start with the first derivative. Well, do you recognize its product rule? Better. At this point, you better recognize that is product rule. Right, so I'm going to treat the 4e to the negative 2x as my first function, and then the sine of x as my second one. So taking the derivative of the first would be e to the negative 2x, but then times a negative 2, and then times 4, so that gives me a negative 8 e to the negative 2x times sine of x, plus just the first times the derivative of sine. So that's a 4e to the negative 2x cosine of x. Yeah, there you go. First derivative, boom. We also need the second derivative because of this d squared. So the second derivative, oof, product rule twice. All right. I'm going to treat this guy as the first one and this guy as the second one, so that I've got derivative of e to the negative 2x would be a e to the negative 2x, but then times a negative 2 times negative 8 would give me a positive 16 e to the negative 2x, and then just times sine of x, plus the negative e to the negative 8e to the negative 2x times derivative of sine is cosine. So that's I guess I'll just already put the plus sign. So negative e to the negative 8 times e to the negative 2x times cosine of x. Then a plus. Now I'm going to do the same thing, but over here I'm going to treat the 4e to the negative 2x as the first guy, and then cosine of x as the second one. So derivative of 4e to the negative 2x, it'll be a e to the negative 2x, but times negative 2, so that's a negative 8 e to the negative 2x times cosine of x, plus derivative of cosine is negative sine, so that'll be a 4e to the negative 2x, and then I ran out of room, sorry, times a negative sine of x. Just so that my parentheses don't confuse you. Yeah. All right. Let's clean this up. Might as well, right? Okay, so second prime, y double prime is, here's a sine of x, and here's a sine of x. So you've got 16 minus 4. So that's a 12 e to the negative 2x sine of x. And combining these two guys, because they both have cosine and e to the negative 2x, it's negative 8 and another negative 8. That's a negative 16 e to the negative 2x cosine of x. All right, so keeping in mind that when they ask you for d squared plus 4d plus 5, d squared plus 4d plus 5 operating on y means second derivative plus 4 times the first derivative plus 5 times y. So that's what I'm about to plug in. All right, second derivative. Second derivative was this guy, so I'm going to have a 12e to the negative 2x sine of x minus 16 times e to the negative 2x times cosine of x. And then a plus 4 times, first derivative was up here. We had negative 8 e to the negative 2x times sine of x plus 4 times e to the negative 2x times cosine of x. And then we have a plus 5 times y. And y was this guy, 4e to the negative 2x sine of x. Yeah. And what we want to know is this guy equal to 0? No. guess I should put equals, right? Because this guy was equal to that, and then that's equal to that. All right, so let's clean it up, yeah? Distribute this 4 inside of there. So I've got a 12e to the negative 2x sine of x minus 16e to the negative 2x times cosine of x minus 32e to the negative 2x sine of x plus 16e to the negative 2x cosine of x, and then a plus 20. I squeeze it in. Did it. Nice. Okay, so what do we got? Let's combine like terms. I've got my e to the negative 2x sines would be 1 here, 1 there, and 1 there. 12 minus 32 would give me negative 20 plus 20. Ta-ta. Bye. And negative 16 plus 16. Ta-ta. See you later. After a while, crocodile. All right, so you get 0. That means that this guy is, this polynomial operator does annihilate the function here. All right, that is it for how to handle it when there's constant coefficients. We'll do when it's not constant coefficients coming up. You guys have a fantabulous day.